Now we turn our attention to the rate of mass accumulation. And again, the unit for everything here will be mass per time, right? Like we looked at, this was mass per time. We need mass per time for rate of mass accumulation. And we know the density of the fluid, right, is rho. So that's the density of the fluid. And what's density? Mass per unit volume. But there are different types of volumes. There is the bulk volume of this cell. Then there is the pore volume, which is where the fluid is stored, right? Because we have grains in the rock. So the fluid is stored in the pore spaces. And so we need to multiply this density by porosity, which is pore volume divided by bulk volume, right? And this density is essentially mass of the fluid divided by the pore volume, right? That's why we need to multiply by the porosity, which is pore volume, divided by bulk volume, which gives you mass of the fluid per unit bulk volume. So here is the mass of the fluid per unit bulk volume. And we're going to need to multiply it by something to get it into units of mass per time. So we need to get rid of the pore volume at the bottom, right? Because right now, this is mass of the fluid per unit bulk volume. So what's the bulk volume of the cell? Delta X, delta Y, delta Z, right? So that cancels this, right? To get mass. But we need mass per time, so we need to divide it by the interval in time for the fluid to move from the left face to the right face, and that's delta T. And so all of this sketch here means rate of mass accumulation will be phi rho volume, delta X, delta Y, delta Z, divided by delta T. Just because that part was rough, I'm going to do it once more so you see that this is mass per unit time. What's pore volume? Sorry, what's porosity? Pore volume per unit bulk volume. What just happened? What's bulk volume? Let's open up bulk volume out. It's delta X, delta Y, delta Z, right? So that's your porosity. What's density? Mass of the fluid per unit pore volume, because fluid is stored in the pore spaces. So that cancels out this. And now you are left with mass per unit volume. And then you multiply that by volume, which is bulk volume, and divide by delta T. So this goes, and the unit of this term right here is mass per unit delta T. The only things you're left after canceling out. So you see everything works out, right? This is mass per unit time. And that is the rate of mass accumulation in the cell. And so if we move on, I'm just rewriting the right hand side again. And now we can divide both sides by bulk volume, right? And these two terms will go. So this is what you're going to have. You're dividing both sides by delta X, delta Y, delta Z. This gets cancelled out. Delta Y, delta Z gets cancelled out. You would have divided by these two, right? So this goes out. This goes out. And what you're left with is precisely, change the color right back to black. It's minus the change in the flux divided by delta X. That's too long. Equals phi rho over delta t. And now we're up to something, right? Because we know from the limits of differentiation, in the limits where delta x tends to 0. So if we take this limit, in this limit we can rewrite this discrete form of the equation I'm missing a change, right? I'm missing a change on the right hand side too. It's change. This is change in this per unit time. I should have pointed out earlier. It's change in this per unit time. That's the rate of mass accumulation. And what's that change per unit time? It's precisely at the current time step minus the same thing at the previous time step. So n plus 1 is current time step, n is previous time step. If we stick to the nomenclature in your slides, this is t plus delta t, and previous time step is t. And that's what we divide by delta t. So just to make that clear, that we're looking at a change in the density of the fluid moving through the system, right? And so when we take these limits, when delta x tends to 0, and also when the time step size tends to 0, that's precisely what delta t is. You can write this equation as partial derivative with respect to x of rho ux equals partial derivative with respect to time of phi rho. And this is your continuity equation for 1D, and the direction is x direction. So we can go a step further and substitute Darcy equation for ux. And what's Darcy equation for ux? It's minus permeability in the x direction, right, over mu partial derivative of p with respect to x. So this is Darcy equation, which you can plug into the continuity equation. You can call this star star. So substituting equation star star into equation star yields minus partial derivative with respect to x of, this is minus, right? And there is a minus outside here. So those two negatives cancel out and this becomes positive. And you have rho, which is this term, times ux, which is what? Kx over mu dp dx. So this is your Darcy equation, equation star star. And right hand side remains the same. And this is the most common form. This is the form of the governing equation for fluid flow in porous medium in 1D. So 1D flow. We've substituted in Darcy equation into this form of the continuity equation. And this equation can be extended out into 3D, pretty much the way we walked through this derivation. So I'm going to use red for the z direction. So for the Z direction, you're going in here, right? The fluid is going in here, and you're looking at this face. So you will get the area of that face, which will be delta X times delta Y. And it's going to come out here. And that's the other face with same area. And what's going in will be rho U Z, delta X, delta Y. All right. That's what you have in there. And what's coming out will be pretty much this kind of stuff, right? But you're going to be looking at UZ, delta rho, UZ, and here is going to be delta X, delta Y. And you can do the same for the third direction, which is what's going in this way and coming out this way. And then this will be UY, this will be UY. Everything else remains the same, right? Delta rho plus delta rho UY. And what's the area in that direction? Is delta X times delta Z. So you see the small changes you have. And when you do that, you will end up with pretty much similar equation but repeated. So this will become, the X direction remains the same. We only add in the Y and Z directions. So the P dx, same as this, plus what you would have gotten for the Y direction. See, it's pretty much in the same format, right? You're going to be differentiating with respect to what? Y. And then same deal for Z. Differentiating with respect to Z, rho K, permeability in the Z direction, viscosity, the P, the Z. And the right hand side really never changes. That's your continuity equation with Darcy equation substituted in for velocity, and that's for 3D. And this is the building block for reservoir simulation. This is the basics for reservoir simulation. We solve this problem in 3D. We're able to predict flow in 3D. And I'm going to stop here for now.